Welcome to secondary steel making course and lecture 20. Today let me restart the lecture about secondary treatment, the primary steel making which was produced, and there are many secondary treatment further refining processes are discussed. But another important aspect with the competitive exams oriented and significance and with respect to the automobile application, secondary treatments, you can transform the primary steel by choosing the suitable treatment with various application route. Let me speak about one such steel, dual phase steel. The dual phase steel is nothing but it is the current emerging trend steel which is called multiphase, or the steel which was transformed into strengthened steel. And this particular steels find application in the car body or automobile industry, which possess high strength and low weight, and you can deform to you will be getting the 100% elongation in this kind of steels. One such steel is a dual phase steel and transformation induced plasticity steel, which I discussed in the last lecture, and twinning induced plasticity steel. And another kind of steels are high strength low alloying addition steel with 5% alloying addition steels, and interstitial free with low carbon content and low nitrogen content steels. These steels find suitable application in car body and which will have high strength with low weight. That is important point to be noted. And what do you mean by dual phase steel? It is named by converting the austenite into the mixture of ferrite and martensite by choosing the fast cooling route, avoiding the nose of the TTT curve. By transforming this martensite with the combination of ferrite, this particular two phases are existing in the steel. Because of this, you will find such high strength and this much elongation. This is the basic composition of the dual phase steel. And another category of the steel, further it is developed, the DP steel is into trip steel, which is transformation induced plasticity. What is the transformation is nothing but phase transformation. Ferrite is from the gamma plus ferrite phase, which was above eutectic temperature. That particular phase is constant and cooled, so that you by choosing the TTT curve route, converting into the bayonet. But also some amount of martensite is some amount of austenite is retaining, which is called retained austenite. The trip steel is nothing but ferrite, bayonet plus retained martensite. After e-treatment, when you go for the cold working process, this retained austenite try to find its way by phase transformation into martensite, which leads to very high strength. This is another important aspect of the trip steel, and the main processing and developing this dual phase steel is being, the temperature is chosen intercritical region, which was around 800 degrees Celsius temperature, kept for long time, is nothing but continuous cooling continuous annealing process, and subsequently chosen fast cooling or rapid cooling, so that it will be converted, the austenite completely convert, around 80% of austenite convert into the martensite, remaining 20% is ferrite. That particular process is chosen to develop dual phase steel, and by doing this particular secondary treatment, why it is being done, these studies are with respect to the application to achieve the high strength, and it should have the low weight, and we need to get large elongation for the car body application. These steels are developed. Those things, one such steel is dual phase steel. Around 800 degrees Celsius temperature, it is initially ferrite and 10 to 20% of austenite, and this particular austenite is converted into the martensite, and after this particular continuous annealing, soaking of around 1 hour, it is been rapidly cooled. This austenite is converted into the martenite, and graphically, for more simple understanding, what is the processing route chosen for developing dual phase steel? This is the chosen steel, which is low carbon steel, around 0.3% of carbon, and chosen temperature 800 degrees Celsius. By doing after trial and error method, this temperature was standardized for developing the dual phase steels, and this is intercritical temperature. After cold reeling, this particular low carbon sheet is sent for the continuous annealing, where it is going to have ferrite plus austenite, and after 1 hour soaking, to avoid the formation of the further ferrite, perlite and bainite, chosen the fast cooling route, so that at the martensite starting temperature starts from martensite and it ends at martensite finishing point, so that you will be having this much amount of martensite, around 20%, remaining is ferrite. This particular steel is developed by this secondary treatment route by taking this primary steel. This is the basic microstructure of dual phase steel. These particular things are the ferrite phases. These things, white phases, are martensite, needle like structure. Notice this particular point. Now let me talk about transformation induced plasticity steels processing route. How does it is done? Basically, this particular steel is developed after the dual phase steel. That is why intermediately I introduced the dual phase steel. Please accommodate in your understanding. And this second annealing step, after same intercritical annealing temperature treatment, another second annealing step is included. For the transformation induced plasticity is nothing but phase transformation of the retained austenite into the martensite and existing with the ferrite and bainite. This route was chosen and developed this steel. This was the basic low carbon steel. After cold rolling, this steel is taken into the intercritical temperature above AC1 temperature, around 750 degrees Celsius temperature, which was austenite plus ferrite, and at this particular stage avoided ferrite phase transformation further and perlite. It is being chosen another annealing treatment, so that bainite will be introduced into the ferrite austenite structure. The bainite is introduced at this stage. Second annealing step is another step in the trip steel. This is basic difference from the dual phase steels to trip steel. And at this stage, again cooled to slow cooling or air cooling is chosen to till room temperature. It is mortar side starting temperature. There was some retained austenite, this much retained austenite around 10% is converted into the mortar side while cold working process. After again further treatment routes. Finally, at the mortar side finishing temperature, you will realize to see the trip steel possess austenite, ferrite, bainite and retained austenite is converted into the mortar side. This is a basic microstructure of strip steel. There is a bayonet phase, retained austenite phase, ferrite phase and martensite or austenite phase, parent phase is going to appear in this. This particular retained austenite is very important in further cold rolling process, further increasing the elongation, further deformation. This retained austenite slowly, gradually transform into the martensite. That is why this transformation is called phase transformation assistance. That is why it is called transformation induced plasticity. At the plasticity, latter deformation stage, that retained austenite is converted into the martensite. On this particular point, it is called the trip steel. This effect is called trip effect. Remember this key point in this topic. Now let me talk about trip steels. Twinning induced plasticity. In the last steel, trip steel transformation, phase transformation of retained austenite into the martensite. Whereas in this steel, twins induced plasticity. The twins are main mechanism point. The steel is annealed around 500 degrees Celsius temperature. The initial intercritical temperature is around 750. Another second annealing step is chosen around 500 degrees Celsius so that you can avoid the converting into the ferrite, perlite and bainite. You can retain or convert the retained austenite into the complete austenitic structure. That is mainly by the formation of twins in this treatment by annealing at 500 degrees Celsius. At this second step, the twins are induced. Twins are nothing but new grains which are evolved in between the parent grains of ferrite and austenitic structure of the starting intercritical temperature. And there was some amount of mill scale. The impurities which were formed during the annealing were removed as a regular practice of developing the trip steel by choosing this acid called HF, hydrofluoric acid. After this annealing process, the composition of the trip steel, twinning induced plasticity steel, is converting the ferrite austenite and the further retained austenite into the complete austenite, so that it is ferrite phase and austenite. The maximum percentage of the structure, the phase is austenite. In between the austenite grains, there will be twins. This is the microstructure of the twins. Twin induced plasticity steel, and basically the austenite crystal structure is phase centered cubic. It is mainly high manganese content steel. The trip steel is high manganese. This manganese content is varied from the trip to trip. For the trip steel, transformation induced plasticity steel, the manganese content is lower, and twin induced plasticity steel higher. Because of this manganese content, the twins are introduced. This is one more reason. and there are some amount of allying additions such as carbon, silicon, aluminium. Because of this aluminium addition less than 3 weight percentage, the stacking fault energy is increased for the tube steel, so that the twins are mainly dominant mechanism. The twins driven mechanism is applied in the tube steel, and this particular tube steel is strain hardening, is mainly it has high work hardening properties. It is mainly because of the dislocations developed by because of these twins. The dislocations are driven, and those are the strong obstacles for the dislocation glide, so that it has high strain hardening coefficient. When you see this stress and strain diagram in the next slide, you will realize that particular point, and it has excellent mechanical properties with respect to the ultimate tensile strength and ductility. Ultimate tensile strength you will see because of this high stacking faults and twins, you will achieve 1 gigapascal ultimate tensile strength. Ductility, it can be elongated 100%, and because of this high work hardening capacity which was induced by twins. Now let me compare few points between the tube steel and trip steel. The high manganese is varying along with the carbon, silicon, aluminium in trip steel and tube steel, and manganese is more in the tube steel and less in the trip steel, transformation induced plasticity. And in case of trip steel, arsenate initially at intercritical temperature it was stable, and as it is been undergoing to further mechanical load and cold working, that particular arsenate, retained arsenate phase transforms into the martensite. Whereas in the case of twin induced plasticity, the dominant mechanisms are twin. There is no phase transformation. The arsenate remains as arsenate, no martensitic phase in the tube steel. Whereas in the transformation induced plasticity, there is a martensite. Remember that particular point also. No martensite, there is a martensite in trip steel, and tube steel have moderate strengths and when you compare with the trip steel, but ductility is higher than the trip steel. That is another point of difference, and the phase transformation in the trip and twinning effect mainly related to the stacking fault energies. This is mainly came because of addition of aluminium. The aluminium addition increased the stacking fault energy of arsenate, and the silicon addition decreases stacking fault energy. The stacking fault energies in the case of twin induced plasticity steels are observed in the range of 20 to 40 millijoules per meter square, and in the trip, in the transformation induced plasticity, it is observed less than 20. So that means stacking fault energy is higher in the tube steels, and the strengths are moderate than the trip steel. These are the comparative points. This is a stress strain diagram comparison for the transformation induced plasticity steel and twin induced plasticity steel. This is tensile stress, this is stretch due to the elongation. See, the area under the curve for the tube steel is higher, but the strength, yield strength is higher in the case of trip steel, and when you compare with the tube steel, but the elongation, you can achieve the 100% elongation in the case of twip steel because of the twins, but you will not get that much. It is around 50 percentage. In the case of trip steel, it is around 50 percentage. Another important point is the trip steel have resistance, high resistance without deforming because of the high yield stress, whereas twin induced porosity steel, even at the low stress application also it deforms, but no breakage. It will not fracture until 90 percentage. That is another distinguishable point. Now comment on the conclusion of this particular point of topic. The twin induced porosity steel possesses high ductility compared to the transformation induced porosity steels. Is it true or false? Please give your opinion. Thank you.